In last class, we discussed about the different types of biasing techniques. In that, we discussed the fixed bias, connected to base bias, and voltage divided bias. Along with, we discussed about the advantages and disadvantages of different types of biasing techniques. Yes. So the ultimate goal of the biasing is to maintain the operating point in the active region, in the middle of active region. Yes. So in that we define the operating point as VC, IC in the C amplifier. This IC value is always depends on the ICO, VBE and beta values. These three parameters are varies with the temperature T value. Yes. So this IC value is stabilized by using the two different techniques. One is stabilization method and second one is compensation method. So connected to base bias and self bias or voltage divided bias are the examples for the stabilization method. Now we'll discuss about the compensation method. So in this compensation method, we'll use the temperature sensitive device such as diodes, transistors, thermistors, sensistors. So by using these temperature sensitive device, we are trying to maintain the operating point or collector current is constant. So collector current is stable by using temperature devices, temperature sensitive devices like diodes, thermistors, sensistors, etc. So we know diodes and transistors, and we are listening new term as thermistor and sensistor. This thermistor and sensistor are two devices, temperature dependent devices. So these two are temperature dependent resistor, thermistor, thermo plus resistor. So thermistor and sensistor, these two are temperature dependent resistors. So thermistor is a negative temperature coefficient. In this, if temperature increases, resistance offered by the thermistor will decrease. And these thermistors are fabricated from the pure semiconductor material. So we know the temperature depends on pure semiconductor. So when temperature increases, intrinsic carrier concentration increases, conductivity of the material increases, then resistivity increases, and resistance resistivity decreases and resistance decreases. When conductivity increases, resistivity decreases and resistance decreases. So in pure semiconductor, temperature increases, the resistance decreases. So these thermistors are fabricated from the pure semiconductor material. And sensistors are the positive temperature coefficients. These are fabricated from the heavily doped semiconductors. In this, when temperature increases, then resistance offered by the sensistor is also increases. So here we will discuss how the temperature affects on resistance of the sensistor device. So when temperature increases, so it is fabricated from the heavily doped semiconductor. Then due to the higher temperature, mobility will decrease. How mobility is decrease? When temperature increases, number of collisions increases in the heavily doped semiconductor. So mobility decreases. When mobility decreases, conductivity decreases, then resistivity increases and resistance increases. So here, when temperature increases, resistance of the sensor will be increases. Clear? So today we will discuss how compensation done by using these diodes and transistors and thermistors and sensors. Yes. So first we station. So we said when temperature increases, this reverse saturation current increases, VB increases, and ICO also increases. ICO, VBE, and beta. These three are increases. These three are varies. Sorry, these three are varies by change in the temperature. When these three parameters are changes, IC also changes. So now we are compensating the change in the reverse action current of collector junction. So here you can observe the diode compensation circuit. In this, we are connecting the diode in reverse bias. Here, the diode and BJT must be fabricated from the same material. So, diode is fabricated from the silicon, then BJT also must silicon. When diode is germanium, then BJT is also must germanium material. So, this diode is connected to keep the IC must constant irrespective of change in the ICO value. So, we know that reverse action current of collector junction is varies with the temperature. Yes. So for every 1 degree Celsius of temperature increases, then reverse saturation current of collector junction increases by 7%. Similarly, here the diode is in reverse bias. Yes. So here the diode is reverse bias. Then when it is in reverse bias, for every 1 degree Celsius of temperature increases, the current in the reverse bias diode is also increased by the 7%. Yes. So now it is compensated. How it is compensated, we'll look into in analysis. So now the diode is in reverse bias. Why? Because the cathode terminal is connected to the VCC or VB, it is positive, and anode terminal is connected to the ground. So now the diode is in reverse bias. So by applying the KVL, we can write I equals to current passing through the RB resistor, I equals to VCC minus VB by RB. So we are considering I is constant. Yes. So it is coming from the VCC. So current coming from the VCC to the RB resistor is constant. So by applying the KCL at base B, then we can write entering current equals to I, and leaving currents are IB and I naught. So I naught is the reverse saturation current, or I naught is the current passing through the diode when it is in reverse bias. So we can write I equals to IB plus I naught. So IB is the base current. From this we can write IB equals to I minus I naught. It is equation number 1. So we know the collector current in C configuration equals to IC equals to beta IB plus 1 plus beta ICO. So 1 plus beta, here beta is a large value. So 1 plus beta is almost equals to beta. So I am replaced the 1 plus beta with beta value. So we can write IC equals to beta into IB plus ICO. So here I am replacing the base current IB equals to equation number 1 I minus I naught. So IC equals to beta into I minus I naught plus ICO. So we know when temperature increases, both reverse saturation current of diode and collector junction of BJT must increase. Yes. So here minus I naught plus ICO, these two are cancelled to each other. So if 1 degree Celsius of temperature increases, then reverse saturation current of BJT increases and reverse saturation current of diode is also increases. So in this equation we are having the beta into I minus I naught, minus I naught plus ICO. So these two will be cancelled by changing the temperature. Yes. So it is approximately same value. Why? Because this diode is from same as BJT fabricated material. So what are the reverse saturation current in the diode? It is almost equals to the, it is approximately equals to the reverse saturation current of collector junction. Yes. So base and collector is also looks like a diode which is in the reverse bias. So the magnetic current in the base to collector is almost equals to the base to collector is almost collector base is almost equals to the diode current, diode reverse bias current. Clear? These two will be cancelled. So from this I naught and ICO, this ICO change in the ICO is compensated by the diode current, diode reverse bias current. So that's why it's called diode compensation circuit. So by cancelling these reverse current changes in the diode and collector junction, so I is constant, so IC equals to beta into I, so it is almost stable. Yes, even change in the ICO that will be compensated by the reverse bias current of diode. So we are keeping the IC is constant by using the diode compensation, but here IC is depends on the beta value. If change in the beta, again IC will change. So diode compensation provides only reverse cycle current ICO but not beta value. Yes. So in this you can observe the thermistor circuit. This thermistor is indicated with the closed resistor symbol. Here it is represented with RT value. So thermistor is a negative temperature coefficient. When temperature increases, the resistance offered by the thermistor is decreases. So here thermistor is connected to keep the IC constant irrespective of the changes in the reverse cycle current of collector. So we know VB equals to VB minus VG. So VB equals to VB minus, instead of VG we can write I into RG value. Yes. So here we need to observe the two conditions. Initially, when temperature increases, the reverse saturation current of collector increases. When reverse saturation current of collector increases, collector current IC value increases. This is effective one. In second case, when temperature increases, the resistance offered by the thermistor decreases. Why? Because it is a negative temperature coefficient. So the current passing through the thermistor is IT. It is increases. When resistance decreases, current increases. We know. Yes. When current IT increases, then what happens? Current passing through the RE resistor also increases. Yes. So I increases. When I increases, then what happens? Voltage drop across RE resistors also increases. So the current passing through the RE, so then voltage drop across RE also increases. When RE increases, that means voltage drop across the RE increases. What happens? In this equation, I into RE value is increases, then VB value must be decreases. From the equation 1, when I into RE, it is nothing but voltage drop across RE increases, VB value must decrease. From the characteristics of CE amplifier, input characteristics of CE amplifier, it is drawn between the VBE and IB value. Yes. So when small change in the base to emitter voltage, IB value has more change. Yes. So when VB decreases, IB value decreases. When IB value decreases, again IC value decreases. So in effective 1, increase in the temperature, IC value increases. In effective 2, increase in the temperature, IC value decreases. So these effective 1, effective 2 both are opposite to each other. So they cancel each other and IC current or collector current is stable even changes in ICO value. Clear? This is thermistor compensation. Thermal runaway. Thermal runaway, it is the self-destruction process, self-destruction of BJT. Otherwise, it is a process of self-damage of BJT because of overheating at collector junction due to the dependent of IC upon ICO value. Yes, we already defined the thermal runaway. When temperature increases, reverse saturation current of collector junction increases. When reverse saturation current of collector junction increases, then collector junction increases. When collector junction increases, the power dissipation at the collector junction is also increases. Yes. So every transistor has defined with the maximum power dissipation rating. So it is defined by the manufacturer itself. So when it is more than maximum power dissipation rating, then our transistor will damage. Yes. So when IC increases, power dissipation factor at IC collector also increases. When power dissipation increases, then it is in the form of heat. So heat produced at the collector junction is also increases. When heat increases, what happens? It is like again temperature. Heat increases, then temperature increases. Temperature increases and again heat increases, again heat increases, temperature increases. So here when temperature increases, power dissipation at concentration is also increases. So if this cycle repeats large number of times, then what happens? More power will dissipate than the maximum rating power at collector junction. Yes. So due to this reason, overheated and vegetable damage. Yes, this is called thermal runaway. Yes, this thermal runaway is also called as secondary breakdown. Why? Because collector junction is breakdown region. Yes, thermal runaway occurs mostly in power amplifiers. Why? Because in power amplifiers, the transistor is operated at the higher values of collector current and VCU values. That's why this thermal runaway will mostly occurs in the power amplifier circuits. This power amplifier can be avoided. Sorry, this thermal runaway can be avoided. How can you avoid? When heat produced at the collector junction must be less than the heat is dissipated at the surrounding. So that's why in the collector emitter base regions, the collector region size is more. Yes. So when suddenly more collector current produces or passes through the collector junction, so more heat will produce. So to dissipate that or to transfer that heat into large region, that's why we are choosing the collector size or collector region size is very large. It is used as a heat sink. Yes. So whatever the manufacturer given the maximum power rating at collector junction, it should not exceed it. Yes. When it exceeds the maximum power rating of collector junction, then more heat will produce at the collector junction. Yes. So due to this reason, thermal runaway will occur. To avoid this thermal runaway, the rate at which heat is produced at the collector junction must be less than the rate at which heat is dissipated to the surroundings or transfers to the surroundings. Then only we can avoid the thermal runaway. Yes, this is about thermal runaway. Thank you.